Hello everyone and welcome to the fifth lesson of Unit 3 on Kinetic Molecular Theory. Kinetic Molecular Theory explains gas behavior by connecting particle motion to measurable properties like pressure, volume, and temperature. Gas particles move in a constant random motion and collisions with the container walls create pressure. Using particle models and graphs, we can relate microscopic motion to macroscopic gas laws such as Boyle's law, Charles' law, and the ideal gas law. All right, so let's start off with a practice question. Why does a higher temperature result in a faster reaction? So we know from our previous lessons that temperature affects the rate of reaction because as temperature increases, so does the average kinetic energy of the particles. This means that the molecules or the reactants are moving around a lot quicker, which means they're going to result in more frequent collisions, and that's going to increase our rate of product formation. So if we're looking at these answer choices, it would be increase the number of effective molecular collisions. Gas particles have a lot of energy and are always moving, and because of this, gases don't have a fixed shape or volume. They essentially spread out to fill whatever container they're in. There's also a lot of empty space between those gas particles, and that's why gases are so easy to compress compared to solids and liquids. In a gas mixture, each type of particle, like helium, nitrogen, oxygen, or argon, moves around independently, and they collide randomly. This motion is going to explain gas pressure and connects directly to ideas like partial pressures and all of the gas laws that we're learning about. So the big idea is essentially gases are made up of fast-moving particles with a lot of space between them, and their motion is actually a way to explain the properties that we observe in real life. Gas pressure comes from particles colliding with the walls of their container. Every collision adds a tiny push, and together these pushes create pressure. We can measure pressure in different units, and the most common are atmospheres, millimeters of mercury, and torr. By definition, 1 atmosphere is equal to 760 millimeters of mercury, or 760 torr. Let's practice with a quick conversion. If we have 657 millimeters of mercury, how many atmospheres is that? Well, we are trying to get to atmospheres, and we want to get rid of millimeters of mercury. So we know in 1 atmosphere we have 760 millimeters of mercury. So we can cancel out that unit, and we are left with atmospheres. And if we take 657 and divide 760, you get 0.865 atmospheres. The ideal gas law describes the relationship among pressure, volume, temperature, and moles for an ideal gases. And the kinetic molecular theory describes gases at the level of individual particles. So the kinetic molecular theory essentially has 5 main points. Number 1 says that gases consist of molecules or atoms in continuous random motion. Number 2 says collisions between these molecules or atoms in a gas are elastic, which means those molecules are not gaining or losing energy when they collide with one another. Number 3 says the volume occupied by the atoms or molecules in a gas are negligibly small, and that's because they take up so much space, so the relationship between the actual amount of space the molecules take up to the space that the whole gas takes up is just really small. Number 4 states the attractive or repulsive forces between the atoms or molecules in a gas are negligible. And number 5 says the average kinetic energy of a molecule or atom in a gas is directly proportional to the Kelvin temperature of that gas. So not all gas particles move at the same speed. Some are moving really fast, some are moving slower, and some fall somewhere in the middle. The Maxwell-Boltzmann curve shows this distribution of those speeds. The peak of the curve is where most of the particles are moving, and the spread shows the range of particle speeds. I like to think of the area underneath as the amount of the total gas. So if you're looking at that cold gas, the room temperature gas, and the hot gas on the screen, those all have the same amount of particles. It's just where those particles are in terms of energy. So the cold gas, almost all of the particles are at the same energy, where in the hot gas, they are spread out. So you have more of an average of types of energies in your particles. This connects to kinetic molecular theory because gases are always in random motion. Their average kinetic energy depends on the temperature, and the collisions spread out the energy among particles. So the Maxwell-Boltzmann graph is really just a picture of how kinetic molecular theory works in real gases. So first, let's look at the left blue curve on this Maxwell-Boltzmann curve. At lower temperatures, because it's a colder sample, at lower temperatures, gas particles have less energy. And the Maxwell-Boltzmann curve is tall and narrow, meaning most of the particles are moving at that same average speed, which is pretty low. At higher temperatures, looking at the warmer sample, the curve is going to flatten and shift to the right, and that's going to show particles having a wider range of speeds because more particles have higher kinetic energy. The peak of the curve always shows the most probable speed, while the entire area under the curve represents all of the particles in the sample. So as temperature goes up, particle speeds are going to spread out, and the average energy of the gas is going to increase. Exactly what kinetic molecular theory predicts. So let's do a practice AP FRQ. A student is doing experiments with carbon dioxide. Originally, a sample of gas is in a rigid container at 299 Kelvin and 0.7 atmospheres. The student increases the temperature of the carbon dioxide in the container to 425 degrees Kelvin. Describe the effect of raising the temperature on the motion of the CO2 molecules. Increasing the temperature, remember, for the particles is going to increase the average kinetic energy, which is why when you raise the temperature, those CO2 molecules are now going to collide with the container and with each other more often. Also, if you want to think of number one, the change in temperature on that Maxwell-Boltzmann curve we just talked about, if you were to raise the temperature, remember the curve is going to flatten and go to the right because now more of the molecules have a higher kinetic energy and are moving faster. Number two says calculate the pressure of the carbon dioxide in the container at 425 degrees Kelvin. So with this, we're going to use Gay-Lussac's law because we have pressure and we have temperature. So our original temperature and our original pressure are in the question, and our final temperature is 425 Kelvin. So we know Gay-Lussac's law is P1 over T1 equals P2 over T2. Remember, for AP Chemistry, you don't actually have to know the names of the laws. I'm just saying them because we're used to saying them in our class. But we are looking for the final pressure, so we're looking for P2. So remember, whenever you're doing these types of equations, you want to rewrite it just to make sure you have all the correct variables. The cross multiplication that does not involve the variable is in the numerator, so P1, T2, and then whatever is left is in the denominator, so T1. So P1, our original pressure, is 0.7 atm. Our original temperature is already in Kelvin. And our final temperature is also already in Kelvin. So we want T2 in the numerator, so it's going to be 425 Kelvin. And in the denominator, we will have 299 Kelvin. So when you do that, you get 0.995 atmospheres. And that would be your answer. And then number 3 says, in terms of the kinetic molecular theory, briefly explain why the pressure of carbon dioxide in the container changes as it's heated to 425 Kelvin. So we know that raising the temperature is going to increase the average kinetic energy of the particles. And we know that particles colliding with the walls of its container is going to increase pressure. So if we increase temperature, we're also going to increase pressure. And we know that because temperature and pressure are Gay-Lussac's law, and those variables are directly related, meaning as one increases, the other one also increases. All right, so let's do a multiple choice question. A rigid metal tank contains the oxygen gas. Which of the following applies to the gas in the tank when additional oxygen is added at a constant temperature? I want you to think about two things from this question. The first one is that it's a rigid container. Rigid container means the volume is going to be constant. It cannot change because of the type of container it's in. The other thing I want you to notice is that it says constant temperature. And if we are at a constant temperature, we know that the average kinetic energy or the average speed of the molecules is not going to change because that can only change with temperature. So let's look at these options. A says the volume of the gas increases. Well, that is false because it's in a rigid container. B says the pressure of the gas decreases. Well, if we're adding more molecules, that means we're going to have more collisions, which would increase the pressure, so B is incorrect. C says the average speed of the gas molecules remains the same, and we know that that is the correct answer. But let's go ahead and go through D and E, just in case we have a better one. D says the total number of gas molecules remains the same. That's not correct because you're adding more oxygen to the container. And then E says the average distance between the gas molecules increase. Well, since you're adding more molecules in the same amount of space, it's actually going to decrease the distance between the gas molecules. So C is our final answer. All right, and for our last question of the day, equal numbers of moles of helium, argon, and neon are placed in a glass vessel at room temperature. If the vessel has a pinhole-sized leak, which of the following will be true regarding the relative values of the partial pressures of the gases remaining in the vessel after some of the gas mixture has effused? And remember, effused just means escaped through a pinhole-sized leak. So if we're talking about the partial pressures of the gases remaining, and we have a very small leak, we know the smaller molecules are going to escape first. So looking at helium, argon, and neon, helium would be the smallest, and then argon would be the biggest. So in theory, you'll have more argon than you would neon or helium, and you'd have the least amount of helium because that could escape the fastest. So that would mean A is your answer. All right, I hope that video helps you. If you have any questions, please let me know.
Have a great day.